Welcome to this lecture series in linear algebra. In this lecture, we'll look at nilpotent operators and apply the things that we develop to endomorphism over complex vector spaces. And let us recall what we need or what gives context to this lecture. So previously, we had seen that complex endomorphisms are upper triangulable, meaning any endomorphism on a complex vector space, finite dimensional, admits a basis or or has a basis over which its matrix is upper triangular. So there is a basis which kills a lot of entries in the matrix, in the sense that a lot of entries become zero with respect to that particular basis. So such a basis kind of gives us a better handle on the endomorphism, since its matrix is rather sparse. In this lecture, we'll prove something much more than that, something that is much more powerful than that, in the sense that even a lot more many entries will be zero. So we'll show that there is a basis with respect to which many entries of the matrix will be zero. Okay, and the main tool that we will use is the cyclic decomposition theorem. All right. Here are some problems for practice. And now let us get started. So we want to define what are nilpotent operators. So fix an endomorphism on a vector space V. We say that the endomorphism is nilpotent if some power of t vanishes. Okay, so that's the definition. We'll look at examples, but let's observe a few things before we go to examples. So note that t is nilpotent if and only if. Let me write it in a different way. T is nilpotent if and only if the minimal polynomial of t is x to the k for some k. So here I'm assuming t is non-zero, because otherwise, to take care of the zero endomorphism, perhaps I could just write k is at least zero. Anyway, so that's the definition. That's a small observation. Why is this equivalence true? Well, if t is nilpotent, then there is some k for which this happens, and therefore the minimal polynomial of t must divide x to the k or some positive k, and hence the minimal polynomial itself should be simply a power of x. So this implication is clear, and this implication is immediate. If the minimal polynomial is x to the k, then t to the k vanishes immediately by definition of the minimal polynomial. Okay, so this is a simple observation. And now, as a consequence of this observation, we have that t is nilpotent if and only if t transpose is nilpotent. So why is this? Well, this immediately follows from the fact that the minimal polynomial of the transpose of t and that of t are the same. So that's it. Some observations about nilpotent endomorphisms. And now let us look two examples. The first is the following. Let t be defined as it takes a vector in C4 to this particular vector, where we kill off the last two coordinates and kind of shift the last two to the first two. Whatever, that is the definition, and you can easily check that t square is 0. So t is nilpotent. A sort of a more elaborate family of examples is furnished by considering upper triangulable operators, or just pick any upper triangular matrix, any upper triangular square matrix with only zeros on the diagonal gives rise to a nilpotent operator. When I say operator, I just mean endomorphism. It's the same thing. It's just a synonym of an endomorphism. Gives rise to an nilpotent operator on the coordinate space. So here when I said matrix, I meant a matrix over the complex numbers, but it could have been over any field. But just to keep things concrete, I have written complex numbers. So why is this? Well, first of all, given any n cross n matrix, one gets an endomorphism of C to the n because that matrix can be thought of as the matrix of a linear transform with respect to the standard basis. So there is a unique linear transform whose matrix with respect to the standard basis is the given n cross n matrix. So any n cross n matrix gives an endomorphism of this guy. And if there is only zeros on the diagonal, then what that means is that the only eigenvalue of this endomorphism is 0. Because the eigenvalues of any upper triangulable endomorphism is same as the entries on the diagonal of the matrix of the endomorphism, provided this matrix is upper triangular. So what I'm saying is I'm just recalling a fact we proved. If we have an endomorphism, and suppose there is some basis with respect to which the matrix of T is upper triangular, then the eigenvalues of T are precisely the entries on the diagonal of this matrix. And since the endomorphism arose from an upper triangular matrix to begin with, the only eigenvalues of this endomorphism will be the entries on the diagonal. But we have already hypothesized that the only entries on the diagonal is 0. And therefore, the only eigenvalue of the endomorphism is 0. And since it is an endomorphism over the field of complex numbers, this endomorphism, the minimal polynomial of this endomorphism must be of the form x to the k, because there is no eigenpolynomial of degree greater than 1 over the field of complex numbers, right? So that's it. I mean, I'm sure you follow. So this is a general family of examples of nilpotent operators. And with that, let us move on. So here is the main fact that we want to prove. Given what we have already established about cyclic spaces and whatnot, this is an immediate fact, but let me prove it from first principles. So what are we claiming? We are saying that if we have a nilpotent operator and V is an arbitrary vector, and here we are not even assuming anything about the base field is arbitrary, we are saying that the dimension of the cyclic subspace generated by V is the smallest non-negative integer which satisfies this equation. So this is something you should be able to prove for yourselves by now, but we will give a full proof in full detail. A corollary of this fact is that if D is the dimension of the cyclic subspace, then this thing is a basis of the cyclic subspace. So this implication I leave as an exercise. It is immediate. Okay, so now let's give a proof. Okay, so let K be smallest such that this is the case, and let D be equal to the dimension of the cyclic subspace generated by V, and we want to show that K and D are equal. So we haven't said anything, we have just restated the proposition. So now, since the cyclic subspace generated by V is by definition the span of V, TV, T square V, and so on, and since so even before I complete this proof, note that such a K exists, meaning this is a non-empty set. Why? Because T is a nilpotent operator. So this set is non-empty. So I should have said that, and therefore taking minimum makes sense. Okay, so what I was saying was this span is equal to this span, because T to the kv is 0, T to the k plus 1v is 0, T to the k plus 2v is 0. So everything beyond the kth power is 0. I mean, including the kth power and beyond is 0. So we have, the span doesn't change if you drop those things. So this immediately shows us that D is at most K. This space is spanned by K things. So the dimension of this space, which is D, is at most the size of the spanning set. So to finish the proof, it suffices to show that V TV up to t to the k minus 1v is are linearly independent, right? Because once these are linearly independent, that would mean that the dimension of this is same as the number of things here, which is same as k. Okay. All right. So suppose we have some linear combination which vanishes. Some linear combination that vanishes. We want to show that each AI is 0. Right? Just restating the condition for linear independence. So now let me show why A0 is 0, and you can complete the proof once I do that. All we are doing is we are applying t to the k to both sides, or t to the k minus 1 to both sides. Right? So all we did was we just applied t to the k minus 1 to both sides of this equation. So the right side is clearly 0. I may write it as such. And when you push this guy in, this term gets, this is killed because t to the k minus 1 composed with t is t to the k, but t to the k kills v. And any higher power of t also kills v, so this much will die out. On the left side, we'll have A0 t to the k minus 1v is 0. But t to the k minus 1v is non-zero because k was smallest with this property. So this is non-zero and hence A0 is 0. And you can finish. Similarly, you can show that A1 is 0 and then A2 is 0 and so on. So I leave the remaining part of the proof to you, and this is the corollary that we want to take away. If D is the dimension of the cyclic subspace generated by V, then this is actually a basis of this, and in the course of this argument we have proven it. So just keep that corollary in mind, and now let us proceed. Now our job is very, very easy. So this is our first preparatory lemma towards the Jordan normal form, which is what we want to prove with or show in this lecture. So fix a complex vector space and T be an endomorphism on it. Assume T is nilpotent. Then there is a basis B of V such that the matrix of T with respect to B looks particularly simple. So there are these blocks, so to say. Everything outside these blocks is 0, and each block looks like this. So each block is also very sparse. Most of the things in each block are 0, except only the things above the main diagonal are non-zero, they are 1. So we are saying that there is a basis B of the vector space V such that the matrix looks particularly simple, where each block is of this form. So it's just that various blocks may have various widths. This block may be 2 cross 2, this may be 3 cross 3, then you could have 5 cross 5, and then again a 3 cross 3. So some sequence of width. Anyway, but each block is particularly simple. And why is this? Well, the proof is just use cyclic decomposition theorem. So then you will be required to show only when you have a cyclic subspace. Basically, these Jordan blocks are coming from the cyclic subspaces in the cyclic decomposition. And since every cyclic subspace has this kind of thing as a basis, by virtue of the nilpotence of T, the matrix of the endomorphism with respect to this basis looks like that. You can easily check, and that's it. That is the proof of this particular lemma. Okay, stay on it until you fully get it, but this is very, very simple, given cyclic decomposition. Okay, so the next preparatory lemma is as follows. This time we have a complex vector space and an endomorphism on the vector space. And we are assuming that T has only one eigenvalue. So when T was nilpotent, this hypothesis was still true because the only eigenvalue of nilpotent operator is 0. But here we are kind of relaxing that a little bit because we are not assuming that the eigenvalue is necessarily 0. It's just that there is only one eigenvalue. So then we want to say that there is a basis of the vector space such that, again, the matrix of the endomorphism with respect to this basis is of this form. There are these blocks. Everything outside the block is 0. But any block, again, looks particularly simple. This time, instead of zeros on the main diagonal, we have the eigenvalue on the main diagonal. And on the super diagonal, this is called the super diagonal. Just above the main diagonal is what is called the super diagonal. Super diagonal is 1 throughout. So how do you prove this? You just first notice that this is nilpotent. This is nilpotent because what is the minimal polynomial of T? Since there is only one eigenvalue, the minimal polynomial of T has to be of this sort. Because T is something over a complex vector space, there is no non-trivial eigenpolynomial, meaning every eigenpolynomial is of degree 1. So once we mention that there is only one eigenvalue, the minimal polynomial must look like this, and hence this guy is nilpotent. Now you apply the previous proposition to this guy, and you will find that this is true. So that's the proof of this thing. And now for the Jordan normal form, fix a complex vector space and an endomorphism on it. Then there is a basis B of the vector space such that the matrix of T with respect to this basis is again of this form. There are these blocks where outside each block you get 0. But any block looks like this where lambda is an eigenvalue of the endomorphism. Right? So we are not here, there is no hypothesis on there is only one eigenvalue or not. Nothing, no such thing. It's just that every Jordan block, so these are called Jordan blocks. So every block here, it looks like this, where lambda is an eigenvalue. That goes without saying because what are the things on the diagonal? The things on the diagonal will precisely be the eigenvalues of the endomorphism because this is an upper triangular matrix. So anyway, even if we don't say that lambda is an eigenvalue, it is forced. So the only difference is that this time you may have different Jordan blocks featuring different values on the main diagonal. Right? If the endomorphism has two different eigenvalues, say, then two different Jordan blocks will exist with different entries on the diagonal. Okay, and this is an immediate consequence of the previous proposition along with the primary decomposition theorem. Once you apply the primary decomposition theorem, you are essentially restricting yourself to subspaces such that over each subspace, when you restrict T to such subspaces, there is only one eigenvalue. Right? So just hit it with primary decomposition theorem and use the previous proposition, you will get this. This is called the Jordan normal form. Every endomorphism on a complex vector space admits such a basis. And note that this is saying much more than just saying that there is a basis with respect to which the matrix of T is upper triangular. We are saying a lot more than that since nothing above the super diagonal is non-zero. So only a very thin strip here features anything of interest. Everything else is 0. Okay, so this is the end of this lecture. As usual, like, comment, share, subscribe, and I will see you next time.